Good morning, everybody. So we're going to continue on with Unit 1 notes. Today we're going to talk about some energy things, and then we're going to get into diagram heating and cooling curves. And again, most of this shouldn't be new. So today we're going to start with energy. And this is the first time I've recorded like this year, so let's see how this goes. So, how do we define energy? The energy is the ability to do work or transfer heat. So that's how we're going to define energy. Now, the question is, what's work? Well, work, and we use a small w for work, is the energy transferred when a force is exerted on an object and causes a displacement of that object. Okay, so for example, if I take my pen, right, and I pick it up, I am doing work to that pen. Okay, I am displacing it. Now there's a formula, W equals F times D, and those of you that have had physics, which should be all of you, you've used this formula before. So our work equals force times distance. I am not going to bore you with doing some problems, some work problems, okay, so those are pretty simple, but that's how we define work. So we need this work definition to go along with what energy is. All right? Well, right along with work, we need to define heat. Heat is the energy, oop, that pen's dying, is the energy used to cause the temperature of an object to increase. Pretty simple. All right. Well, let's go on and talk about kinetic energy. Kind of bleeds through, so I think we'll go to a new page. Kinetic energy is your energy of motion. And remember, kinetic energy is usually KE. You'll actually also see it like this. E subscript K. Okay, you should recognize both. Now, Atoms and molecules are always moving. Now, we talked a little bit about particle motion last lecture. All right, so remember, the particles are always moving, and no matter what phase that they're in. So if they're in a solid phase, okay, the particles are only vibrating. Okay, solids and liquids are vibrating, rotating. In a gas, they're vibrating, rotating, and translating. Okay, however, okay, no matter what the temperature is, no matter what their temperature is, there's always some sort of particle motion. Now, there is a magic point where we think all particle motion stops, and that's absolute zero. Okay, now, we've never reached absolute zero, but absolute zero, we're theorizing that all particle motion stops. But since we can't get to absolute zero, particles and atoms always are moving, right? Which means they always have kinetic energy. There is a formula for kinetic energy. Kinetic energy equals 1/2 mv squared. And again, this is another equation that I'm sure all of you have used. Okay, so if we need to calculate kinetic energy, this is what we'll use. Well, how does that relate, actually? How do we relate this kinetic energy to temperature? What is a substance's temperature? Well, it is the measure of the average kinetic energy of a substance. Or of its particles. Okay, so when we have a sample, okay, the particles are going to have different amounts of kinetic energy. So when we actually take its temperature using a thermometer, we are getting the average kinetic energy of that sample. Okay, so now we will be using, most of the time we're going to use the Celsius and the Kelvin scale. So I have, here's an quick view of our thermometers. So we're going to be using the Kelvin scale. Okay, we're going to use the Celsius scale, and we use the Fahrenheit scale, and you do need to convert, and I will give you those conversions. All right, so remember the Kelvin scale and the Celsius scale are actually the same exact scale. The only difference is what we call zero. In the Celsius scale, freezing is 0, and the boiling point, the freezing of water is 0 degrees Celsius, and the boiling point of water is 100 degrees Celsius. We use the same change, okay, and 1 degree K is equal to 1 Kelvin. The only thing we do with the Kelvin scale is instead of making the freezing point 0, we decided to say, hey, it makes more sense that in the Kelvin scale, we're going to use absolute zero as 0. Okay, now remember, absolute zero is negative 273 degrees Celsius. So if we switch this scale, 0 is absolute zero. The freezing point of water is 273 K, and the boiling point water is 373 K. All right, now, I don't have any Kelvin thermometers. We do have Celsius thermometers, and you'll have to convert back and forth. Now, we are used to the Fahrenheit scale. Water freezes at 32 degrees Celsius, it boils at 212 degrees Celsius, right? This is a 180 degree interval versus a 100 degree interval over here, right? So there are more degrees, okay? So if you change 1 degree Fahrenheit, it's a small change compared to 1 degree Celsius. Okay. Now, okay, we're not going to use the Fahrenheit scale. Okay, we will stay in this metric system. Okay, so we'll use the Celsius scale. So you do need to do some conversions. So Kelvin is equal to degrees Celsius plus 273.15. Okay, 273.15. Most of the time we will skip the 1.5, but if we have significant figure issues, you may have to use that. Degree C is equal to 5/9 degrees Fahrenheit minus 32. Degrees Fahrenheit equals 9/5 degrees C plus 32. Okay, so these are your conversions from Celsius to Fahrenheit and Fahrenheit to Celsius. This is your conversion between Kelvin and Celsius. So this gives you those numbers so you can do those conversions. Okay. Let's talk about potential energy. And potential energy is stored energy. That arise from the attraction and repulsion an object experiences in relation to other objects. If I had to guess, this is a different definition for potential energy than most of you have ever had, and we're viewing this in a chemistry perspective. Okay, so for example, okay, when we have, let's say that we have a molecule of methane. Okay, there is an interaction, there's a bond between the hydrogen and the carbon. Okay, this is storing energy. There's an attractive force between this carbon and hydrogen, right? And that attractive force is actually storing energy. And if we're storing energy, okay, that is potential energy. Okay, so we're using a little bit different definition of potential energy. All right. Now, for this whole unit, or for the whole year, okay, we're going to be in the metric system. Okay, so you're going to need your SI units, and I think I posted this. I think this is on Classroom for you if you need it. All right, so these are our bases. Okay, so our mass time, mass, length, time, temperature. So we got grams, meters, seconds, Kelvin, moles, amperes. Okay, so you can see these, all right? And then here are all your prefixes, all right? You do need to be able to convert from one thing to another, okay? And I'm not gonna go through that, so you should be able to go from nanometers to meters and meters to kilometers and all that kind of stuff. We'll talk a little bit about dimensional analysis tomorrow, all right, where you're gonna be doing that. All right, but here are your SI units. Okay, and this is posted under your reference section, I think, on Google Classroom. Okay, so we need to kind of pull all this together, and we're going to do that. Yes, we're going to pull yesterday's lecture and today's lecture together. And to do that, we're going to use potential energy diagrams. No, I lied. We're not going to use potential energy diagrams. Sorry, I'm lying to you already. Just haven't had enough coffee yet. We're going to use heating cooling curves. So basically, I'm going to make a big graph here. We're going to label it. And this is nothing new. Okay, it's the same thing you had last year. Okay, so we've got a big graph. The heating cooling curve looks something like this. Okay, comes up here like this, and then it levels off. Right, and then it might come up here like this, and then it levels off, and then it might come up here like this. Over here is temperature, and it's usually in degrees C. Okay. Remember, this is a measure of our kinetic energy. Down here, usually it's time, or it can be in energy, so we could be in joules. All right, now we need to be able to label this thing. So remember, this is a graph. So just for fun, let's put some check marks in here, and technically this is an illegal graph. You could never ever do this. Okay, and we'll do the same thing this way. And we'll label this -10, -5, 0, 5, 10, 15, 20, 30, 40, 50. And I don't know, maybe this is in seconds, and we'll 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Whatever. Okay, so we have our setup. All right, so let's go ahead and start labeling this thing. All right, so this first slant is where we have a solid. Okay, second is a liquid. And third is a gas. Now you can read going up, you can read coming down. Okay, so if we're going up, okay, if we're going in the up direction, this plateau right here is melting or fusion. Okay, so we go from a solid to a liquid. Okay, now we're warming a liquid, we add heat, okay, temperature is increasing, eventually we get to this plateau. This is where boiling or vaporization occurs. All right. Once we have all boiled or boiled or vaporized the water, we have all the gas, and the temperature of the gas increases. We can also come down the chart. So as we come down, we're cooling a gas, we're removing heat, cooling gas, temperature goes down. Okay, this is the condensation point. This is where condensation is occurring. We're converting from a gas to a liquid. We cool a liquid down. Eventually reach this magic point. This is freezing. Solidification. Or crystallization. And then, so we crystallize, and then we get back to a solid. Okay, now, notice where temperature is changing. Okay, temperature changes when we are in phase. Temperature does not change while we are in changing phase. Okay, the temperature doesn't change here, the temperature stays constant here. All right, so we have a solid, we add temperature, the kinetic energy increases, we add heat, temperature goes up, we reach the melting point. That whole time that it's melting, the temperature stays the same. Okay, so in this area right here, we have both phases. We would have both a solid and a liquid. It would continue, as long as we're adding heat, it would continue to Melt, if we start taking heat away, it would go back this way. Okay, if we added heat, it would go back this way, and we increase temperature until all of it has melted. Once all of the solid is melted and we have all liquid, the temperature starts to rise again, and the particles vibrate and rotate. Okay? Once we reach this point, we've reached the boiling point, the particles start to translate, okay? And again, temperature stays the same that whole time that we're boiling water off, or boiling any substance off, excuse me. Once it's all a gas, the temperature can increase again. Okay? Now, other things that we can get from this graph, we need to be able to label our energies. Okay? So, where is kinetic energy changing? Well, kinetic energy is changing where the temperature is changing. So on the slants are where we have our kinetic energy changes. So KE is going either up or down on this slant. Kinetic energy is either going up or down when it's a liquid. The kinetic energy is changing either up or down when we're a gas. Now, why do I say up or down? It depends which way in the graph we're going. If we're adding heat, the kinetic energy increases. If we're taking heat away, it's going to decrease. Does kinetic energy change during phase change? Well, the question is, does the temperature change? And that is no. So during our phase changes, our kinetic energy is staying the same. It remains constant. Now, the other energy we have to deal with on here is potential energy. And here's why. As we're going from a solid to a liquid, we continue to add energy. And because of the law of conservation, we have to take into account where that energy is going. It can't just go poof into nothing. It's got to go somewhere. Right? So during phase change, we're changing potential energy. Okay, so as we go from left to right, we're adding energy still, but the temperature's not changing, so our KE stays the same, but we are increasing potential energy. So during our plateaus, our potential energy is going up or down. Well, what about potential energy in our slants? PE is staying the same when kinetic energy is changing. It's the exact opposite. Okay, it stays the same. Right, so, which of the three phases has the most potential energy? Well, this gas right here will always have more potential energy than a liquid. A liquid will always have more potential energy than the solid. Okay, good. Some other things that we can get from this graph, we can actually get the melting, freezing point, boiling point, condensation point. Okay, so for this substance, if we come up here, this is where we're freezing and melting. If we come back, this substance is freezing or melting at 5 degrees C. And it's dependent on whether we're adding energy or taking it away. So it freezes and melts at the same exact temperature. If we're adding heat, it's going to melt. If we're taking heat away, it's going to freeze. Same thing up here. Okay? If we come up here and we extrapolate across, this substance is 25, I don't know, what do you think, about 27? This is going to boil. It's going to boil or condense at about 27 degrees C, and is dependent on whether we're adding heat or taking it away. All right, so what other things can we get here? The slopes of these lines mean something. The slopes of these lines mean something. And the slopes are telling us how easy or how hard the substance is to heat up and cool down. Okay? If it takes a lot of energy to heat it up or cool down, okay, it's going to have a shallow slant. Okay? If it doesn't take much energy at all, okay, it's going to go up pretty quick. All right? So it's much easier to heat this solid than it is to heat this liquid. Same thing with these lines. Okay, the length of the line can tell us how hard or how easy the substance is to freeze or melt and boil and condense. So it takes this whole time to freeze and melt the substance. Okay? It takes this time to boil and vaporize. So it's actually easier, it's harder to melt and freeze than it is to boil and condense. And that's typically not true. Okay? That's typically not true. Okay? And we'll talk more about that when we actually get into some math. Right, so you should be able to handle this heating and cooling curve. All right, that's all I have for today. You have a little bit of work posted and we will continue on. I hope things are going well. Have a good afternoon.